this is just water. So here we have some acid. I'll move this over here so John can see.
There we go.
So we have some acid, and we can just start adding water to it. We're probably gonna have to add a lot of water, but as we add water, since water is pH 7, if we add enough, we will actually start to get to closer and closer. I'm gonna need a lot of water. And I'm also gonna grab some baking soda. Show you what we do with that. Sodium carbonate.
I'm just gonna stand back and freeze baking soda in there.
So if we add enough, we should actually see the pH go back up towards 1. It might take a long time. There we go. Well, that's pretty satisfying.
That is crazy how it is.
It's turning, turn to amber, so.
Apple juice.
So when we compare the amber to the scale, right? On this this little scale here, amber is now is now in the 5s. So we're if we just tip a little bit of that off. This is why you don't use drinking glasses as reaction vessels. Okay. And if we keep going.
That was turning slight green. What the?
We should get back to 0, right? Back to 7.
6 now.
Between 6 and
Yeah.
7, yeah.
Right. Now, I don't know what the pH is out of this tap. We might have some tap problems where the pH of the tap might be a little low, but
Not B7.
now I can give it a little darker so you can see it a little nicer. Now at this point, if I keep adding water, will the pH keep going up?
Yeah.
Well, what's the pH of water?
7.
7. We're at 7, right?
Oh.
So as I add more water, I can't actually make it blue. I can only make it more water.
Yeah, there's not
So
gonna
it
be
just
any
stays.
There's no hydroxides here to add, really, right?
Yeah.
I could ruin the whole thing by adding like 1 drop of this sodium hydroxide, or a few, and you can see those purple drops kind of spreading, and now the balance is broken, and now my balance is gone
is gone to
purple again. So now I'm up to 13 again.
Yeah.
So that's sort of the magic of these things. So if in doubt, add water to clean up. Right. So if you have an acid, if you have some acidic solution and you're worried about it, you can add water, and that's usually a safe bet. But notice we did have to add quite a bit of water just to get a little bit, and only a few drops of acid or base, and we get the same problem. So instead, if you had a similar problem with like some acid spill here, and I'm just going to give it a little drop of water just to fill the bottom. So you can see the acid spill. It's acidic, it's red in color. I could keep adding water, but I'd have to add a lot. But if I do have some sodium bicarb or some sodium carbonate on the side of beside, I can throw some of that in. So this is like baking soda.
Oh. Okay.
And so that baking soda, turned it.
Strong.
It's actually pretty strong.
Strong acid, then it turned to.
Yeah, stronger than I expected it to be, for sure. I was hoping for neutral. So that was my hope.
So don't use
It's
water.
still
Yeah.
high 13.
It's pretty high, yeah. It's a little higher than I was expecting it to be.
Strong.
So maybe I went a little too heavy on my sodium carbonate. It might settle down a bit.
Anyone want Kool-Aid now?
Yeah. So that's always fun. Now there's a lot of different compounds you'll find if you have ever if you ever clean up after you've had some blueberries and you put some blueberries in the sink, you'll notice a really dark color. But then as you add water, the color will actually suddenly change to like a red. And that's because a lot of dyes are natural indicators. So the color of a dye is usually affected by the pH of the solvent. So you can get things like a blueberries. Blueberries is one I've noticed a lot. Red cabbage has a pH, changes pHs, changes like from purple to pink or something.
Strawberries should have it too.
Strawberries might, yeah. Like most dyes will have some sort of color change if you change the pH. So adding a little bit of, and there's a lot of like mixologists and stuff who play with these sort of things and like making the color in some sort of beverage change by adding some juice. What is it? It's there's this magic tea you can get from David's Tea. And when you add a drop of lemon juice, it changes color. And that's all because lemon juice is an acid.
Because of the citrus acid.
And so that citric acid, that causes, or acetic acid there, that causes a change in the concentration. Or the change in the concentration of hydrogens and hydroxides, and causes that sort of action to happen.
Yeah, the reason why I mentioned strawberries is because if you cut one open, it's whitened on the inside.
Mm-hmm. That might be because of the difference in the cell types, but
Yeah.
but that also could be that they might be making those proteins and those colors. So that's fun with indicators. So get an infinite screen going here. Okay. All right. Oh, now this is falling asleep. Okay, so the news of the day, of course, is that we are going to be shut down next week for classes. Your classes will be all moved on to YouTube. So I will still, I think my last class and I agreed that it would probably be best if I had a scheduled class.
Yeah.
Still, so at the 10 o'clock time, I might be in my pajamas, but I will still have a live stream, and it'll be for the whole week. Maybe on Wednesday or Friday, I can't decide which day's better, but one of those I might post a meeting link instead on Classroom, and that will take you to Google Meets or Google Hangouts, whatever, and that's like a site where we can have sort of a video conference. So you just follow the link, and I don't think you have to log in or anything. You might have to, maybe you have to log in. But you can.
Jerome has his going through Google Classroom.
Oh, he has the meetup happening inside a classroom.
Yeah.
Okay, good. So yeah, so once you're, I guess, if you've logged into Google Classroom, then the login will be exactly the same. So yeah, so if he's doing the meetups, we're gonna try to do one of those meetings as well.
Okay.
So yeah, so if you're in Jerome's class already, you might have already played around with this Google Meets. We'll try to do one of those a week as well, just to have a chance for you to talk back a little bit, not just in the chat. But anytime during the live stream, please feel free to use the chat to talk to me, and I will take your questions and check them out. Feel free to turn your cameras off on Google Meets if you want. I know some people, that was the number one concern in the last class. It's like, oh, I don't want a camera on. I'm like, I don't want a camera on. So. But we do what we have to do. The Google meetings are not saved, or I'm not planning to save the Google meeting, so that's why we'll only do it once in a while, and we'll do the live streams all the time, because at least then the questions are saved.
So
And stuff.
live stream, when we do live stream, we can just watch you and ask.
Yeah, if you want to ask questions, you can type them in. Yeah, it's just I can't hear you. That's all. So that's why I want to still do a meeting once in a while.
I was gonna check it out to see if I could watch it on off my Xbox.
Yeah, I guess you probably can.
Yeah, we
Yeah.
have YouTube on there, so.
You have YouTube. Yeah, if you can find my user, then yeah, that seems possible.
Well, I could just use my phone and.
Oh yeah, then you can send the stream. Yeah, use the little. Oh, that's funny.
I was thinking,
But I don't understand, Kate, a lot of people, like here, students and teachers are not infected.
Yeah.
But we still have to take at least 3 weeks off.
Yeah,
precaution.
I mean it's a precaution because I do think that even yesterday I even saw a teacher yesterday walking around with coughing and sneezing, and I was like, wait a second. So, like we don't really know which is coronavirus, which one's, like if you might not even
Just
feel
the
sick.
average cold, yeah.
Yeah, so there's that's the biggest problem, is that like people could be carrying it right now without knowing it. And if you have children, like your children might not have any symptoms, and then but they could be carriers for it.
Yeah.
So there was a big. It looked like schools was like one of the major ways that they're spreading. So
Well, I noticed.
it's a little different. It's interesting about this building because already our students don't.
Well, I mentioned it, I brought it up with the post office even, and they said, I think it was on Monday, they said, yeah, we sent one of our supervisors home and one of the carriers. I'm like,
Yeah.
holy geez, it's like the carrier is outside.
Yeah, but it can survive for up to 3 weeks on surfaces. So you might receive a package and it could even have it on it. So it's
Even
like,
out shopping, you see a bunch of people sneezing into their hand and touching their phones. And
yeah.
it's
Yeah, it's-
everywhere.
Apparently, cleaning your phone is a super important thing right now, where people don't think about how often they're touching your phone. I like let someone look at a picture on my phone, and afterwards I'm like, oh, I should probably clean this now.
Yeah.
I like clean my phone with like really strong alcohol, and then all the back came off of it, and I'm like, oh, it was ruined the whole finish on the back of my phone.
They slightly overdid it with this virus.
Well, one conclusion I liked was that someone said, we will not know if we overdid it. We will know if we underdid it. Because if we underprotected, then of course the result is going to be bad.
Especially if it's spreading that fast.
If it's
I was
overproduction
making
stuff.
fun of all those people that stocked up on toilet paper. Next thing you know, all the lumber yards are gonna be bare. Because we need,
Not a bad idea. Yeah.
because we're gonna go back to using outhouses, maybe, I don't know.
Well, I keep seeing posts on my social media that are people who had like construction jobs halfway done, and then now the construction workers are gone. So they're like, this one guy was posting how he was paying for his bathroom to be renovated, and now he doesn't even have pipelines for water, and it's his only bathroom in his apartment. And I'm like,
Oh my god.
oh no, what are you gonna do for the next 3 weeks? Like,
When you build another house out there,
You-
lock up.
Yeah.
YouTube, the finish of it.
yeah, exactly. Okay, so that's how we measure. Now, one thing we didn't play with is the phenolphthalein. This is a word that haunts me to this day. I had an exam where I had to spell this correctly, and if I didn't spell it correctly, there was no mark. It was like a second year course in university, and it said like spell, provide the names of all reagents you used on this lab, which was like 3 months before. I had to remember all the reagents, and then if I didn't spell any of them, if I spelled any of them incorrectly, I was like,
Oh
So-
my god.
like phenolphthalein, like
Yeah, you
Terrible,
keep
man.
on repeating it, it's like, then you get to that day, it's like,
yeah.
what the heck?
So phenolphthalein is a pretty common indicator test. Indicator in phenolphthalein, the indicator changes color as soon as you hit pretty much neutral. So it is. I'm trying to figure out in there. Okay, right. I don't need to see that. I need to see this. So it will be an acid. It will be in acid. It will be colorless. And in a base, it will be pink. So it's colorless at pH below 7. And over at about pH 8, it will turn pink. So what we do is we often will add that to a clear reagent, and we'll slowly add base to it. And then as we add base, it'll reach that pH 7 point, and we can figure out how much it looks like. So here's a picture of what that pink looks like. It's quite pink. And we'll maybe if we get a chance later, we'll play with it. And it's it's fun. I like Universal Indicator, but Universal Indicator has a lot of because it has so many different colors. It can be difficult to exactly estimate what pH you are. This one, the color change is so distinct that it's very, very commonly used for neutralizing chemicals.
It's the same one, John, that we find in Dollarama, no?
I'm not sure.
It's,
Maybe.
It's white ball, like, they call it phenolphthalein.
Yeah, then that would probably be it. Yeah, I don't know what do they sell it for.
They use it for, to get away the flies, the small,
All those little.
Oh.
flies and
Yeah.
stuff.
the same name, yeah. the same.
For fruit flies?
Yes. No, if it's so old, just.
I don't see something about it here, but I'd be interested to look into that. Yeah. It might be from also a family of chemicals too that might be similar but with different uses. Blue litmus paper is the easiest one to remember. Blue for base. So blue litmus paper doesn't change color; it stays blue in a base, and then turns red in an acid. This can be like a sort of a paper you might carry out in the field with you. Not something you would do like any analytical chemistry with or anything careful. You take this with you as you went out into the world, and you're testing water samples, for example. And the two types of paper just are blue and red, and they're very simple to use. This blue paper will turn red if you're in an acid, and this red paper will turn blue if you're in a base. And so I'm seeing if I can find one that's been used. And it's also very cheap, so that's kind of like why it's very popular. Anyways, that's kind of the idea, is that you.
That's testing for like waters and stuff.
Yeah, these are all bad examples. You're not supposed to actually put it in your liquid. Anyways, supposed to take a drop of it out and then touch it. Oh, here's a nice picture. So here's a picture of blue litmus paper touching a lemon, and notice that where that's touching the lemon, it's turned red.
Yeah, the acid's turning it red.
How does it
Yeah.
turn red until it's in the orange?
Yeah, it doesn't turn red until it touches exactly.
Yeah,
Exactly.
It doesn't change on the skin area, the skin.
Yeah, so there's not a lot of acid in the skin. It's mostly the acetic acids in the fruit, so that's where it'll change color. Yeah, indicators are fun. Here's another one where someone put. Here you can see that these are nice because in both cases one paper is blue and one paper was red.
Yeah.
But now you can see that they both are the same color. This one, the bottom is turning blue to match. This one stayed blue. Here they both changed blue. Oh, actually, this must be pure water. So this one didn't change at all. This one didn't change at all. And then in a base, they both change. In water, they don't change. In acid, they'll both change red. They'll stay red if they're red already.
The blue and the red are pretty much almost the same. So red turns.
Yes.
So red will stay red,
and then
and then blue will turn red. And so we talked about some other types of acids and bases we see. This is an important note here that the pH scale is in a base 10 system. This is a little bit of a tricky system to work with, but every one of these numbers is actually like writing 10 to the power of that number. So 7, it's not 7, it's like 10 to the power of 7. It's actually 10 to the power of -7, which is even harder to wrap your head around, but anyways, it's a 10 to the power system. So And that means that every one of these is an increase or decrease by 10. So this is well, that's not a good example because that one, so this jump here, this is times 10. That's like 10 times stronger. So milk of magnesia, I believe this is something you can take as an antacid.
Yeah.
Ammonia cleaner, you're not drinking that, right? If you can't help it. It's like,
Because you have the base combined with the acid right there.
yeah, the ammonia as a cleaner is just a really strong base.
Yeah.
And so, but this is a 10 times jump. To jump from borax to milk and magnesia, and borax is something you might add to your cleaning if you have in your washing machine. You might add some borax, but
I
milk.
use that actually for a good little home remedy to get rid of ants.
Oh yeah.
Yeah,
It's supposed to be really effective
with
against them.
some sugar and then mix it with water.
Yeah.
And then put cotton balls, soak them in it,
Oh,
and then let them dry and then put them around your house. The ants will come and take it, thinking it's just sugar,
right.
I guess, and then take it back. And then
Yeah, they taste that initial sweetness.
Is that the one that the kids play with it?
Yeah, you can also make a. You can make
Yeah, is
a.
the one?
Yeah, with borax. Yeah.
But there were a lot of kids that were coming back with
Yes,
chemical
yeah, we
burns
have
and
it.
stuff.
Yeah, that was one story. Yeah.
Yeah.
One woman let her kids play with borax unobserved, and then now borax is banned from all schools. So the little girl got all these chemical burns on her hands. But me and my boss both, we when I was a PhD student, we did a lot of work in boron, and so we worked a lot with boric acid and borax, and we were both like, I can't even understand why they would think it's so dangerous. Well, essentially, I mean, he had 20, 30 years working with boron and was like, boron's not dangerous. And it's like, but it is, we figured it was probably an allergic reaction, but it looked like
Yeah.
chemical burns. So now schools ban borax. They can't make slime anymore in schools. They now make it with much more expensive, you can use eye cleaner or eye drops.
Oh yeah, that's
Yeah.
really.
Maybe it's not concentrated.
But in eye drops, it's borax again.
Yeah.
If you look at the ingredients of the eye drop, it's borax, but it's just diluted.
Yeah.
So if you dilute anything, it's safer, right? So, anyways, I'm not going to get on my high horse about borax and how safe it is. But yeah, it makes a great slime.
I just know.
Yeah, I love that great slime. And I used to do a lab with kids in grade 6 every year, and we would have them come in and would make slime. And I would give them sort of the basic instructions, and then they work with their parents to figure out what kind of recipe they wanted to use, and then they
So
would make
there's
it.
a recipe for the borax.
Yeah, you make it. It's like it's just you try to dissolve as much borax in hot water as you can, and then you add glue.
So you did mixes or not? So it doesn't-
I mean, it's basic, so you do want to be careful. You're not handling it too much before it's mixed, but and don't let kids go crazy on borax. It is basic, and if they have sensitive skin, especially, then but you really only need like a teaspoon of borax mixed into some water. Use hot water at first to get it really dissolved, and then just add a little bit of glue until it becomes slimy. Keep stirring. If you add too much, you get like a rubber, which is cool, but it's not really it's like a rubber that kind of snaps. It's not it's not as much fun as the slime. Use hot water, you get nice like slime. We used to always use cold water because I didn't want the kids using hot water. It works okay.
Some ideas for.
Yeah, that's right. Yeah, maybe I'll have to start posting some fun chemistry you can do at home stuff.
Yeah,
You know?
exactly. Some stuff you can do for kids.
Yeah. Very fun experiments are like food experiments. I love food experiments. Make three sets of muffins and use different amounts of one ingredient. Use half the right amount and then double the amount and see what happens. Baking soda is especially exciting. You make some really terrible baking soda muffins at the end, but but the middle and the low ones are not bad. You can eat those. That's just doubling your baking soda does kind of make it gross. But it is really cool when you see your muffins come out and you've got one that's really tall and then one that's really middle and one that's short. So if you can control that somehow, it's pretty exciting. But yeah, there's definitely going to have to find some things to keep my kids busy, I guess. Other than interrupting my streams, which I'm sure is going to happen. So here we can say that tomatoes are 10 times more acidic than coffee from our scale. This also means that pH only becomes very dangerous in the extreme ranges. It becomes more dangerous on the base range, so sort of around that borax range, you can start to get some, that becomes a sort of entering the danger zone. Danger zone. Over here, we really don't have very much danger until we're, sort of in the lemon juice area. This is the human danger zone, of course. Animals have different danger zones a little bit. Fish, for example, probably have a much narrower danger zone. Because they depend on the water to provide them with oxygen and to provide them with other features. They're going to be their range could be smaller. Birds and stuff like that. Birds don't really interact with many liquids, so they might not be prepared for higher low pHs. Even your dog, your dog can have their hair can be sensitive to the pH of the soap you use. That's why they make dog soaps and stuff, so that they have different
They
pH
also
range.
have that, fear of for children's soap, stuff like that.
Right, as you grow older, you get a little bit more hardy towards different sort of pH ranges, or
Yeah,
more comfortable living with dry skin. I guess I don't know. So, yeah, your eyes are less sensitive. Both acids and bases are dangerous, but it's all about concentration and the nature of the chemical. A low concentration strong acid may be as dangerous as a more concentrated weak acid. Some acids are not very strong, but still dangerous for other reasons. The word acid doesn't mean bad, but it does mean be careful. Remember that because humans are mostly proteins and fats, bases are more dangerous to us at lower concentrations. So that's why our danger zone for bases is earlier. Right, danger zone is only 100 times stronger than water, whereas the danger zone for acids is now 10,000 times stronger than water, because it's 2 compared to 7. So that's 5 increments. That's 5 zeros. So 10,000 times. This is only 100 times. So
We were talking about high concentration. It's about adding water. That's it.
yeah, so think about the when I started adding water to my acid, right? If I took a very dangerous acid and I kept adding water to it, eventually it reached a zone that I could have drank it. There wasn't any other chemical reason that HCl was dangerous to me, so I could have actually drank that water, and it would the danger was actually the universal indicator at that point. That probably was probably not very good for me, that coloring agent, but. The HCl part, once you added enough water, it wasn't actually particularly dangerous. And my body has HCl in it. And so if you reduce the concentration enough, then it becomes safe enough to work with. It's also why we don't like to let students just, use full concentration acid, right? If we bring the concentration down by 10 times. So often for students, we like to give them 0.1 molar HCl, which is 10 times weaker. So then for HCl, which normally starts at about a 1 or a 2, if we give you 0.1 molar, we're bringing it back into that 3 range, which is like apples. It's like apple juice at that point. It doesn't taste like it, doesn't feel like it, but it's apple juice. It's as strong as apple juice. So by concentration, concentration can also reduce the danger. Vinegar, for example, right? Vinegar is right in this 2-3 range. So, but that's pure vinegar. We don't often drink pure vinegar. You'll add it to some potatoes for some, fries in vinegar and mix it. You don't usually, but if you started drinking pure vinegar or pure lemon juice, your mouth would get all full of sores and you'd feel it wouldn't feel great.
I used vinegar for heartburn.
Yeah.
Like,
Oh, really?
Like not a whole lot, but like maybe a teaspoon or 2. And it would help calm my stomach down.
Interesting. I wonder why that would be.
I don't know, that sounds that weird.
Yeah, I guess it's a little lighter than stomach acid.
Was also another one too?
Mm-hmm. Yeah, I mean, lots of people have, sometimes you find something that works and it works. So we do have a type of reaction. I guess we'll get into this type of reaction. Maybe we can get into it right now. That's pretty close to the end, isn't it? Well, it's about halfway. What else is there? Oh yeah, pH and soil. Okay, so we get into some environmental stuff next. Is anybody missing the environmental science book? Did anybody? You haven't gotten the environmental one? Okay, I have them downstairs. I think on my desk. So
I gave one out yesterday, so you get one now.
yeah, I gave out 2 different booklets. Oh, actually, you know what? I have exactly 2 copies. If you want them in booklet form, I also have them in booklet form.
No, this is it.
Oh, I have do you want a physics booklet in yellow?
Oh,
Or do you like a whole?
what is that? This is
Same.
Okay.
This one just has a lid on it.
Oh, it's-
My printing finally came, but it's like so many days later. Okay, so let's do these neutralization reactions. They're very fun because they're simple. So they are the idea that we take an acid and a base, and if we combine them, we will produce a salt and water. And that's always going to be the same. Once you learn a couple of these, there's really only so many options for this type of reaction that we're going to do. So we're just going, this is called neutralization. When I perfectly matched my sodium hydroxide and my HCl, I could possibly hit that perfect neutralization point where it all goes to be just water and salt. And in fact, at that point, it would be safe to drink. So that's one way to work with it. So provided the base and salt don't have other things that are dangerous. Something like beryllium hydroxide is never going to be safe because beryllium is super toxic for you. Or mercury hydroxide, you can neutralize the mercury hydroxide,
Yeah,
but the mercury's still there.
there.
Yeah, exactly. Yeah. There's a couple other really nasty elements here that are never safe. Chromium's never really safe.
All staff are asked to check their email for an important email about Chromebooks. Thank you.
It's interesting.
Is that?
I don't care about that
sea
email,
salt
actually.
Or is that table salt?
So it'll depend on the nature of the reactants. So if it was sodium hydroxide and HCl, you would get NaCl, which is table salt, and sea salt. Sea salts will have a lot of other elements in there too, but
And the thing with salt, you could add that to, like, if you're making pasta, it could actually bring out the flavor even more.
Yeah, and that's sort of another property of salts that they bring in. If you add enough salt, you can lower your melting point, or your boiling point, so you can increase the boiling point, so you get your water boil higher. It's a lot of salt. So salt is a general word. It just means the mixture of a metal and a non-metal. So any ionic compound generally kind of falls under the term salt. So anything from over here mixed with something from over here, usually that's going to be called a salt. Salts, yeah, I think that we can just generally say it's any ionic compound is a salt. I don't think I'm lying to you if I say that. I'm trying to think of an example that breaks that rule, but I can't. So yeah, so any ionic compound is a salt, and we're always going to form some ionic compound when we mix an acid and a base, and we're going to make some more. So let's write an example here. We have hydrochloric acid and sodium hydroxide. So off of our tables above, we can find that hydrochloric acid is HCl. This is one you'll have to sort of memorize eventually. And sodium hydroxide, which is NaOH. When these two combine, what we're looking for is we want to take the OH part and the H, and we put them together to make a water. That's H2O. And then we want to take the other component, which is the sodium and the chlorine, and put those together. So this is our salt, and this is our water. Right? This is, of course, now a double replacement reaction, like we discussed earlier, because we had two chemicals that were previously partnered with two other chemicals, and now they have joined up into a new partnership. So previously we had a green and a purple in each of the compounds. Now we have the purples together and the greens together. So they've done a swap.
So you have to switch them around when you're redoing them, like from the CLNA. You have to switch it at the end to the NaCl.
Oh yes, yeah. So what I'm looking at here is it was on the left already,
Yeah.
left and right, and so it stays on the right.
Okay.
Yeah, so it stayed on the right and stayed on the left.
Okay.
The water one is a little weird because we always put hydrogen on the left of oxygen unless it's in something, it's doing something else. Okay, so let's try another one out. So here we have hydrofluoric acid mixed with a calcium hydroxide. We have to be a little careful here because notice that calcium hydroxide has two hydroxides. So we're getting a pair of hydroxides. So we're going to, we know that our products are going to be, so we are looking for something that looks like this. We know that we're going to get water. And then we also have to figure out what's going to be the salt. So the salt's going to be these other partners, right? The calcium and the fluorine. And this is where we go to the back of our periodic table and we think about charges again. So I'm going to do my thinking color, which is going to be gray, 2 plus and 1 minus. Those are on the back of your periodic table.
Yeah, because there's the positive 2 back there, so calcium's positive.
So how many fluorines am I going to need?
You're gonna need 2 to balance it.
We've got it. And then we can clean up. And so now we have the calcium fluoride. So now we can go back and we can think about how do we balance this whole thing. I've got 2 fluorines over on the right? I have 2 of them. So I need to fix that by putting a number here. What number should I put there? Big old 2.
Yeah, you put
So
2 there. It
Probably
balances
purple
out
on red is not great.
it balances out the hydrogen also.
And it happens to balance out the hydrogen. You're right. Yeah. So that worked out well. And now, did it balance out my waters though? No, I do need 2 waters because the oxygens are not balanced. That one would have been tricky to see, but see the 2 on the oxygen. So I needed to balance that. Okay, that was a tricky one to start with, but looks like they're going to keep going with that formula. Looks like we're running out of time. So I think I'm going to leave us with one more example here. So we have water, and now we're going to be mixing barium and a sulfur. We're going to go look at the back of our periodic table. Barium is 2 plus, sulfur is 2 minus. So it's evened out, perfect. So I can just get rid of those. And now I just check my water to see if it's balanced. I have
1 of each.
1, 2, 3, 4 water, 4 hydrogens here, right?
You have,
Yeah.
Yeah.
So if I put a 2 in front of that water, I'm probably pretty good. Cool, done. All right, have some fun with that this weekend. See if you can finish the rest of that sheet, which was only 1 more. Oh, there's more. There's practice on the next page. There we go. Whew. All right. So there's some practice questions there. Maybe I'll go do a little bit of review of that on Monday. It looks like we have about 2 more days or so of this unit left because the next section is an environmental section. So that's sort of, we are kind of covering our environmental chemistry section as we go here. But So let's we'll work on that, and then I have I'll start the environmental unit. What my plan is to kind of have about an hour's worth of videos or assignments every day for you. Oh, yeah, you can be online.
I just left this one out because
Great, yeah, that's okay.
I couldn't figure it out, and then I asked him, he's like, it's not on there.
Right, that's the one that was broken, yeah.
Yeah.
Okay. Yeah. So be online. See if there should be assignments and things coming through there. It might be I might use Google Forms a little bit, which is like you just type the answers into the website, or at the very least there'll be the YouTube videos to watch, and we can catch up later when we get back to see what you learned.
So we, yeah.
Yeah. Thanks everybody, and we'll see you
Is it physical?
Eventually.
eventually.